Okay, welcome back. Today we're going to talk about the elimination tree, and the theory starts to get thick. If it hasn't already, it hasn't really already. This is some of the thickest theory of the book. So I left off looking at this idea, which is not a very thick theory. The idea that we can take this graph of the lower triangular matrix L, and remember the whole goal here is we're trying to do these sparse triangular solves, right? And but we'd like to find the non-zero pattern of that triangular solve efficiently. But then there's another issue, is that not only are we doing triangular solve, we're doing a triangular solve, and the result of which is going to be concatenated onto the matrix L itself to compute the kth row of L. So we do a triangular solve, and then that becomes the kth rows. And we start with the kth column of A as our right-hand side to compute the kth row of L. So that led us to these two theorems that said, well, you know, if you have an x in here in the solution that's non-zero, well, that will be non-zero in L because these are the one and the same entry. And then we also know, because of the reachability idea, that if this is non-zero and there's an edge from I to J, then that will become non-zero. And if that is then non-zero, then so is LKJ. And so, in other words, this non-zero and that non-zero cause this to become non-zero. But see, this non-zero is the same as this one. So in other words, these two non-zeros cause that to be non-zero. Okay. So this gives us the elimination tree because we realize that, hey, if I've got these two non-zeros in here, I can ignore this one in my reach. Because if there's one above me, that means there's this two-step hop to the place that this guy is going to take me to directly. So rather than take the shortcut, I can take the long way around, which seems kind of odd. It's like, well, wouldn't you like to have short paths? No, you don't. You just want to be able to search this graph efficiently, and that does not require short paths. It just requires few paths. Okay, so why, we can ignore this edge, and we'll get there anyway, in other words. And so the only thing special about this edge is that it's got another edge above it in the column. It's got another non-zero above it. So anything below here, there's nothing special about it. Anything below this first non-zero can be pruned away. And so if we take a graph that's acyclic and prune away all but one entry, we end up with a tree. So the tree is defined. The parent of a node then is defined. If we have a column J, whoops, I should use the same notation, I. If we have a parent I, if we go to the first off diagonal, so the parent of I is J, if J is the smallest row index such that LJI is non-zero. So that defines the tree. It's very simple. And it just comes out of chapter 3, the triangular solve and then reach and all of that. So we can prune away the graph to get the tree. So here's an example. Here's a symmetric matrix. Here's its Cholesky factor. Now, how do we compute this? Well, we have to compute it. So far, the technique we would use would be to use the row Cholesky method, one row at a time, which is not Cholesky's method, by the way. I used something different, I think. But he didn't compute it row by row with triangular solves, but that's okay. We still call it Cholesky's method, for lack of a better name. And this is the tree. So for example, if you go down from 1 to 6, there's going to be an edge in the tree from 1 to 6. But the edge from 1 to 7 is redundant. We don't need that. Wait a minute, something is... Yeah. We don't need this edge from 1 to 7. And the reason we don't is because if 1 becomes non-zero, and if there's an edge from 1 to 7, then the edge from 6 to 7 will become non-zero. And then sure enough it does. This becomes this X becomes a non-zero. It's fill-in the matrix A. So there's an edge from 6 to 7. So why bother with the edge from 1 to 7? If I want to know what's the reach from 1, I can start at 1 and go to 6, and I'll find 7 because 6 points to 7. The parent of 2 is 3. The parent of 3 is 8, and so on. The parent of 4 is 6, etc. So this factor L has a very special property. If you look at the graph of L plus L transpose, you get a graph which is referred to as chordal. That is, every cycle longer than length 3 has a chord. If you have a cycle in a graph like this, every cycle of length 3 or more will have a chord. And so this will have a chord as well. So there's a lot of very important combinatorial properties about the graph of L. Unfortunately, inside the factorization methods in MATLAB, all these theorems are exploited, okay, to their fullest extent. The problem, though, comes in MATLAB, and this was a design decision which I would have preferred they not make. They didn't. I wasn't even involved with MATLAB at that time. When they introduced sparse matrices into MATLAB, they decided that whenever they operated on a sparse matrix and returned to the MATLAB workspace, they would prune off all the zeros, right? Explicit zeros. Well, there's a problem with that. What if this entry happens to drop to 0? Okay, then you can't prune this. If you want to use this graph of L later on, so suppose you wanted to do an actual triangular solve. Now, if you knew that the graph of L came from a Cholesky factorization, the tree would just be the first off-diagonal entry in every column. And you could use the tree instead of using that more complex reach and all of that. And you could speed up the code quite a bit. And there's other things you can do with this L because it has very special properties. But the moment you start arbitrarily dropping entries, then all the theorems go away. All the theorems break entirely. And you get something that's a subset of what you could have, but then you can't extrapolate. You can't say, oh, well, this entry would have been non-zero. Well, I guess you could do that, but it takes extra time to do that, and it's too expensive. So it's not. You end up with garbage. So you lose information by throwing stuff away, in other words. Even though they're zeros. They're special zeros. Those dots, those are entries that are important combinatorially. If they happen to be numerically 0, we'll leave them in there because they have combinatorial importance. If you drop them, like you drop this, well, then you no longer have a tree. And all the theorems fail. So that's another reason why it's important not to drop these entries. Okay, so now that we have this tree, we've got to figure out how to compute it efficiently. So the reason being is if we somehow knew this tree ahead of time, if we could have an efficient way of computing the tree, and that's what we'll do. That's what I'll do, is I'll show you. We'll compute this elimination tree efficiently. So the first step will be to compute the elimination tree. From A itself. That's the first step in the algorithm. The second step will be then to find things like the non-zero pattern of L. Now you might think, well, wait, this is backwards. The non-zero pattern of L defines the tree, but I'm going to do it the other way around. Okay. Did I lose the camera? Okay. So I'm going to do it the other way. We're going to do it the other way around because it turns out that this, once all the theorems are done, can be done very, very quickly. Essentially, this is going to be time almost order the number of non-zeros in A. Okay. Then finding the pattern of L, we can do in time order non-zeros in L. We can also do other things. We can find the column counts and the row counts. And what those are different than the pattern, and they're easier to find in terms of time complexity. The row and column counts are how many non-zeros there are in every row and column of L. And that's useful. If we had that ahead of time, we could lay out a nice static data structure, and then we could fill it with all of our values, because modifying a matrix on the fly in an irregular way is difficult, right? We'd like to know, if we could know how many non-zeros are going to be in every column of L, then we can just lay out our data structure and then fill it, and we're done. And there's other things we can do with this kind of symbolic analysis. Once you have the tree, once you have the row and column counts, you can set up methods for doing parallel computing, because now you know that you know where the dependencies are, and so all of this symbolic work sets you up then for the numeric factorization. In order for you to do it efficiently, you can predict where things are going to go, where things are going to be, what work do you have to do, and the stuff up above can be done all in. Except for this thing, finding the pattern of L, although I'll show you how to reduce this as well. But this right here can be also done in time proportional to the number of non-zeros in the original matrix. Almost. This is not quite. There's something rather funny there. There's an inverse Ackermann function. If you've heard of that before, if you're not, it doesn't matter. I'll show you when I get there. So there's a large number of very powerful things we can do with these matrices before we hit the numerical factorization. And then that allows us to set up the numeric factorization. We have something then very predictable that we have to compute. And that's good for many things. For parallel computing, it's good for high performance, even sequential computing. Okay, so now let's look at these theorems that give us a better understanding or better grapple on how it is we could do this. How could we compute the tree? I mean, this defines the tree, and you know how to compute the pattern of L. You just do that triangular solve at each step. Just do it symbolically. Find the reach, and we would be done. In fact, let's see. I could skip ahead and show you, well, I'll not do that. I'll follow the line of the book. But it would be possible at this point to skip some of the more high-powered theorems and go straight to a method that would compute the pattern of L and the tree at the same time. Because think of this as constructed inductively. Okay, and I have a code that does this, by the way. It's very short and simple. And it doesn't use all the theories here in the book. It's not in C-Sparse. So to compute the kth column of L, you need to do this reach. Right? So the non-zero pattern X is the reach in the graph of L of the right-hand side, which is right here going to be the kth column of that matrix A, only in the upper triangular part. Well, the reach of a tree is very simple to compute. And now think about the tree of this matrix here. It'll actually, now when I say tree, I really mean forest, because you could have multiple roots of this tree. So let's suppose we're going to fold all these together, at least fold together all of these steps 1, 2, and 3. It turns out that it's very straightforward to do that with the theories we have so far without going any further into the theoretical work. Okay, suppose I've got the tree so far. I'll call this, and I'll call this also in the rest of the book, t sub k minus 1. Okay, let's let t sub k minus 1 be the tree, the elimination tree of the first, in MATLAB notation, the first k minus 1 leading submatrix of the L matrix. Okay. Now think about how tk and tk minus 1 are going to be related. If you've got a column J here, and there's a non-zero in the first k minus 1 rows, then it doesn't matter what you put down here, it's not going to change. Right? That's the first non-zero. There could be other ones here. It doesn't matter. If you compute the kth column and you find a non-zero there, well, so what? You've already got a parent. Right? So this would mean, I'll call this I instead. So from I to J, it's there already. So if you compute the kth column and you find a non-zero there, there's no extra work to do. There's nothing to do. Okay. The only time that there's work to do is if you have, I'll call this I1. If you have another one, say I2 here, or it could be here, it doesn't matter, left to the left or to the right. It's all 0 here. Now, in that case, I2 will be a root of the subtree, or the subforest, I should call it, tk minus 1, right? So these notions I'm introducing are going to be coming up later. So what tk minus 1 is going to look like is this. I2 will be a root of a subtree. I won't be a root, I1, I'm calling it, won't be a root of a subtree. There'll be another j, but there'll be, maybe j will have a parent, maybe not. You know, maybe this is j, and maybe suppose j has no parent. So j is another root of another subtree. Okay, let's suppose we find, when we do step k, we find maybe there's an I3 over here that's all 0, but then suddenly we find a non-zero here and here, and other ones, but they're not as interesting. Just maybe we find two new non-zeros in columns that we haven't seen before, except for the diagonal. So prior to this, I3 would be the root of its own subtree. And we come across and say, now we know that the parent of I3 is K. So we've joined together two subtrees. Or I could have just had the parent of one subtree if I found just one non-zero, and one new non-zero in a new column that I had not yet seen. Maybe I found 2, maybe I find 10. The number doesn't matter. Maybe I find none at all. But what's happening here, to construct the tree from tk minus 1 to tk, the only thing that changes is you start with the tk minus 1 forest, or a tree. Could be a forest or could be a tree. And you stick above it k. And then k might be a leaf of tk. It might be and I'll use t to denote the entire tree at the very end, which is to say t sub n. If it's the last tree, I'll just drop it and say that's the tree. Okay. So at the kth step, we're putting a new node up top here and potentially connecting it to some subtrees. And so we're folding together trees now, and now this is the graph, or this is the tree tk. And that's exactly the tree we need for the next step of the solve, the next step of the factorization. Right? Because what I'm doing here at each step, at step k, I'm computing the kth column, the kth row of L, and to do that I need to do a triangular solve with this matrix. Well, if I have this matrix, if I have the matrix L, k minus 1 to k minus 1, 1 to k minus 1, if I have its tree, I can compute the reach of any right-hand side. Once I have that reach, I have this non-zero pattern of this kth row, Once I have the non-zero pattern of the kth row, I can ask, well, who's new? What new column have you seen here that yet does not yet have a parent? What new node have you seen that is the root of the subtree tk minus 1? And all those ones that are new, you say, aha, your parent is now k. And now that will never change. Once you have a parent, you're adopted into this family, okay? You never lose your parent. Because it doesn't matter that you see this column again. The least, the row index, the least row index of all the non-zeros in this column will still be k. It's the topmost entry in the column. It's not going to change if you get new entries down here, right? If this isn't clear, please stop me, okay? Because otherwise I'll just keep going, and you'll lose track of what's going on. This is exceedingly important. Does it all make sense? We're just building a tree up one node at a time. Okay. I'm not actually going to use this method. Okay, but this is this is the slower, gentler approach into these theories. So this would be one way of computing the tree. We just do all these reaches one at a time. And we could thus build the tree. Now, so let me just jump ahead and show you this. Here's an algorithm which computes the reach. It does a sparse triangular solve, in other words. Okay, and the algorithm is very simple. And it could be used on a subtree as well. So let me erase this part right here. I'm jumping ahead. I'm pretending that I can either, I'm basically pretending that I'm ignoring the more elaborate theorems, which I've not described to you yet. But I'm supposing that, suppose this is all I've observed combinatorially speaking. Okay, could I use this to actually do a Cholesky factorization efficiently? And the answer is yes. And the time complexity would be reasonable, but we can do better than this. And this is still an important part of our algorithm. But I could actually use this by itself. So what's happening here is we're passing in a matrix A, a column K, and so I'm assuming that I'm going to do a triangular solve of the first. Doing this triangular solve of the k minus 1 with the right-hand side k, all right? And I want to find the reach. And actually, this algorithm, for the moment, let's pretend that it... let's see, do I need to make this pretending? It'll do this by itself because the way it will mark the nodes. Let's see. I'm changing this algorithm on the fly is what I'm doing when I'm making a subtle change to it, and I'm trying to remember what that change was. If we come across, so the change needs to be that I'm actually going to be modifying the parent if I come across, if I hit node K, but I'm not doing that right here. See, this assumes. Yeah, so this algorithm will fail slightly if I fall off the edge of the world here. in a very subtle way. But so let's pretend that doesn't happen. So let's just ask the question, how would we compute the reach of a tree? And we just have to be careful that we don't fall off the edge. So let's suppose I've got a tree. Actually, I don't need to draw it. I can just use this one on the board or in the chalk. Right here. So suppose I've got a tree, and I want to do a triangular solve with this matrix right here. Well, if I want to do a triangular solve with this matrix, I need to do the reach of this graph of L. But remember, I don't have to do a reach of this entire graph. I can ignore all the entries below the first one. So I can ignore that entry, and I can ignore this one, and I can ignore these two, and that one, and this one, and those two, these two here, and so forth. All the entries except for the entries in the tree, I can completely ignore to find the reach. I mean, I could give you an example if you want, but if I say, well, I did this before, I guess. If I start from 1 and I ask, what's the reach? Well, the reach will be 1, 6, 9, 7, 10, and 11. There are other edges in the graph that I'm ignoring. There's an edge, for example, from 1 to 7, but hey, I got there anyway. Okay? From 6, what are the other edges? The other edges go, you notice they only go to the ancestors, from 9 and 10. 6 has an edge also to 9 and 10, but I'll get there anyway. This is another theorem that I'm going to elaborate on. So I've pruned away all of the edges. I have a tree. So now finding the reach in the tree is much easier than finding the reach in the graph. Suppose, for example, I have non-zeros in positions, say, 3 and 7. So I'm doing a triangular solve with this matrix, and the right-hand side, B, has positions in rows 3 and 7. And I want to know, well, what's the non-zero pattern of X? Well, the non-zero pattern of X, I can just read it off the tree. 3, 8, 10, 11, 7, 9, 10, and 11. So what would that look like? 3, 8, 10, 11, and 7, 9, and 10, 11 I have already. Well, but this is not yet sorted. It's not in any particular order. And a triangular solve has to be done in a specific order, a topological order. All right? Or it could be done in a strictly sorted ascending order. I could do 3 and then 7 and then 8 and then 9 and then 10 and 11. That's the non-zero pattern of X, but this implies an extra sort, which I don't want to do. Now the question is, how do I use these two things, and how do I compute this more efficiently without doing the sort? Well, the idea is to exploit paths in the tree. If the data dependencies all go up the tree, they go from 3 to 8, from 8 to 10, and before I do 10, before I do step 10, I have to finish both 3, 8, and 7 and 9. So it doesn't actually matter where we start looking first, node 3 or node 7. I mean, which do you? Well, I'll do both. Okay. Let's suppose in the reach we start at 3. We're going to do both 3 and 7. We start at 3. We walk, and we find all these nodes are unmarked from 3, 8, 10, 11. As we walk up the tree, we're going to mark these nodes. So I'm going to put a note on the tree that says, I've been there before. Okay, so I produce this list, 3, 8, and 10. And I want to push it on a stack. So 3, 8, 10, and 11. So here's my stack. So I traverse up the tree until I see a marked node and stop, or until I fall off the edge of the world. So 3, 8, 10, and 11, and then put it on the stack. You notice that it's put on there backwards. So 11 goes at the bottom. But that's okay. I could traverse the path twice, figure out how long it is, okay, and then traverse it again to decide that, oh, okay, or I could do this in a temporary workspace. I could say, okay, I'll start at 3, and then I'll put 8, and then I'll 10 and 11, okay, and I have a workspace of size n to put this on. Then I stop, and then, okay, I'll stick it on the stack here. So there's the first path. So what happened is I started here and went all the way up to the top. Now I start at 7, and I go until I see a marked node, which is in particular node 10. 10 I've already visited, so why we don't want to visit it again. So I go from 7, and I see 7 and 9, and I'll push this on the stack. And now it turns out that that's a topological order. That's a DFS order. If I go here now, if I do the triangular solve this way, all the edges go from downward. There's no edges that go upward. So it's a topological ordering. So here's one path, and here's another one. And I want to do this in reverse order that I did the paths. So if I traverse this entire path first, then I want to do this last. If I do this work first, numerically speaking, but stop, I've satisfied all the numerical dependencies. Because I can do all this because it doesn't depend on anything happening in this path. Do all this work and then stop, and now go here and keep going all the way to the end. And I can do that because I've done this work. And this work must be done before I do step 10 here. So this is what a DFS would do. If you think about the depth first search as well, if you just did a full-blown depth first search of the graph, what would happen? And you start at node 3. You start at node 3, and then you see, oh, I have one neighbor. Okay, I'll do a DFS on 8. From 8, you'll see 10. You won't see 9 because the arrows only go upwards. From 10, you'll see 11. 11 will finish. 11 will thus finish and get pushed onto the stack you see at the very bottom. And then you return 10. You say, is there anybody else to do? No, because I only have one outgoing edge. So 10 finishes and gets pushed on the stack. And you return and say, well, are there any other neighbors of 8 to do? No. So 8 finishes and it gets pushed on the stack, and then 3 finishes. And we have the same result, 3, 8, 10, and 11. And then we go to the next node of the right-hand side, B, node 7, and we do the same thing. We do a DFS on 7, and we see, oh, I see 9. So I start 9. Do I have any neighbors that are unmarked? No. So 9 finishes, and it gets pushed on the stack right where it exists, right where it should be. And then I finish 7, and I'm done. So there's the topological sort. So I just did the DFS on the tree, but I did more. I mean, we could use the DFS. It's a little more high-powered than it needs to be. We can exploit the nature of the tree and just write a simpler algorithm. Okay. So if you remember from chapter, I guess I don't have the notes here for chapter 3, but computing the reach of an arbitrary graph is, it's that depth first search, and there's the recursive stack you've got to keep track of, and so forth. It's a lot more complicated. But the reach of a tree is much it's much simpler. If we're only doing a triangular solve for k, we don't want to go past k, so we're going to mark that. So I don't want to accidentally go further than k. Which, if I'm building up the tree, I won't be able to do that anyway. Because there'll be, if you will, there are nodes up here, k plus 1 through n. I can't get to them because there's no edges there to those. They're still up in the stratosphere. They're not pulled down to earth. Okay. So this just makes sure that I stop at the right place if I have the tree pre-computed. So and that's why I have here this defined as const. So the parent is well defined. The parent is an array that defines the tree because we just say, for example, that the parent of 3 is 7. Every node has at most one outgoing edge. And if 3 is a root, or in this case, say, what was it, node 11, I think was a root. Parent 11, I will denote as -1. -1 means there is no such. So all I have to do is the triangular solve. I have to I have to start at every node every non-zero in the right-hand side, which is what this traversal is going to do, because the right-hand side is going to be the kth column of the A matrix. I get a row index out. If this row index is larger than k, then that's not an entry of interest, because I'm assuming here that I'm doing the triangular solve for just this piece of the matrix. So I may have a larger matrix that goes further, my A matrix. But I want to ignore that, and I'm assuming that's the triangular solve you want to do. It's just the, actually, if I is, so I actually will look at node, I'll look at K as well, but there's going to be nothing here necessarily. So if I is bigger than K, then forget it. So now I just have to walk up the tree and build this list here, the 3, 8, 10, 11. I want to keep going until I come to either a marked node or I fall off the end of the map. Well, if the tree is already pre-computed, and that's what this algorithm assumes, then I will come to node K. Because if you think about what's going to happen here is if I'm using this column of A to construct the graph of L, this is the Cholesky factorization, L transpose equals A, then if I walk off the edge of the map, that means I will make K the parent. So if I come, where's my subtree here? If I come here, and let's suppose I have not yet computed the tree. This algorithm here assumes the tree is pre-computed. Okay. But you'll see here, there's no check to see, oh, do I walk off the edge of the map? And here's why. Do I walk off and not figure out where I'm going? I mean, you notice here, there's no check to see, well, what happens if parent of I is -1? What happens if you walk off the end of the world? The reason is this. If you come to a node, suppose the tree is not yet computed, and if you come to a node that has no parent, and yet it is not K, then you will make K the parent. Because that will reflect a non-zero here, what did I call it, I2. A column I2 that's all 0 here, and then it's non-zero here because you visited it. It's going to be non-zero in the solution because you can reach it. Okay, you've computed the triangular solve, you get the answer, but then you would make that K the parent of I2 if it's not already the parent. If you don't fall off the end of the world, you'll hit another node. But eventually you'll have to fall off to the end off the end. So eventually all these nodes that you can visit, if you don't visit I1 to J, then J will not be made the parent of K. But if you can reach node I2 and I2 is not K, and if you can fall off the edge of the world here, then you'll make this parent there. And so what this means is you will always stop at node K. If you have the tree pre-computed, then node K is your final termination of every path. You can't get further than that. Well, you could go further if you had the tree here, but you will visit K. Because that's the way the tree got built. So that's why there's no test here to say, oh, wait, what happens if I have no parent? You will hit node K. And if I mark node K as visited, then you'll hit a marked node. You're guaranteed. Because I know I'm going to reach node K, and if I mark node K, that means I know I'll hit a marked node. And I don't have to check to see if I fall off the edge of the world through a node that's a root of the subtree that does not yet have a parent. So that's why this test here, I don't have to test to see if I is -1. I know it won't be -1 because I checked to see if it's marked or not. And I will finish on node K, and that will be marked, and I will terminate if I get that far. So, so we mark node K, and then we walk up the tree, and walking up the tree then just builds this list. Have this temporary array S, which I'm incrementing this length one by one. When I see a node, I put it in the list, and I mark it. That's simple. 2 lines of code. Start with length of 0, walk up the tree until we see a marked node. And walking up the tree, this is kind of a cool little thing in the for loop here. How do you go from one node to the next? I equals parent of I. So there's a 3-line, well, including the curly brackets, it's 5. There's a 5-line loop that walks up the tree of a graph. Walks up a path in a tree. So this will start here somewhere and walk up until it sees a marked node, or it sees node K, which, oops, it's also marked, so I'll walk until I see a marked node. So I walk up the tree and I stop, just as I did here in this example. I walk up the tree and I stop at, in this case, the first traversal, I'll stop at node K. And what I've done then is every time I see a node, I put it in this list S from 0, 1, 2, and 3 from the left. And I see, okay, there's my path. I just build my path. And now I've got to take this path and stick it down here. All right. And the trick is this workspace and the stack can actually overlap. So what I do is I have a workspace of size n here. This is a similar kind of trick as you saw before. If you have a workspace of size n, and any given integer from 0 to n minus 1 can either be in this list or on the stack or nowhere, then the sum total of all those two objects, the list and the stack, can never be more than n. And so they can live within each of they can live in the same workspace here. So if I start by putting 3, 8, and 10, and 11 in this direction, and then I stop because I reach the end. Now all I have to do is take this information, this 7, 9 is not there, and just shift it down to the bottom. And that's what this loop does here. This just shifts one at a time, starting at this one. So it looks like this. I start here and I move the 11 down. And then I go here and move the 10 down. And then go here and move the 8 down. And here and move the 3 down. So it's a one-line loop to move the path from this list here and push it onto the stack. So this is doing a push. It's reversing the order because it's got to be done in the reverse order of the finish times. 11 has to be first, not 3. I could not have put this immediately onto the stack because I can't put 3 at the bottom. I do not want 3, 8, 10, and 11. That's in the wrong order. I've got to reverse it. So I'll put it here in this temporary space and then shift it down, and it's in the right order. Okay, you look puzzled. And then I just have to clean up by unmarking all the nodes I visited. But wait, let me getting ahead of myself. Now, though, I'm not done because I've got another non-zero in the right-hand side that I have to find the reach for, and that's node 7. So I'll start at node 7. I'll grab node 7. It's not bigger than k. It's in the upper triangular part. And I'll walk up the tree, but this time I'll come across a marked node. I'll see node 7, and it's not marked, okay? And then I'll see node, what was it? Node 9, I think. I don't have I think it was 9, wasn't it? Yeah, 9. And then I come to 10. Oh, I've marked node 10. So we stop and put this on the bottom, 7 and 9. So there's my result. That's what I wanted. That's the non-zero pattern of the result. Now, with this result here, let's suppose that, in fact, this assumes that the whole tree is present. But let's suppose all I had was from 1 to 11, t sub 11. Let's see. No, t sub 10. Let's suppose that we take the const out of this. We can actually build the parent array as we go. Because remember now, if I do this triangular solve on the submatrix, okay, let's suppose I do the triangular solve here on the first 10 rows and columns of L. And I'm actually computing, I'm trying to compute the 11th row of my matrix L. Then my right-hand side would have to be different. It would have to be this one, 3, 5, 7, 8, and 10. So 3, 5, 7, 8, and 10. That's rather extensive. So let's suppose I start at 3. I traverse up until I see node 10. And from node 10, I would be at a root. But so I'd have to change this algorithm to say that, well, if you find a root that's not node k, then we know that the next parent, the parent of that node, must be k itself. And that's because we come to a node here. We come to, say, node 10 that had, it's the last row, last column, I'm sorry. It had yet no parent. And yet, I found, when I did the triangular solve, I found a non-zero there because I'm at node 10. Or, for example, if I come up to, well, this is kind of a boring example because it's always stopping at node 10. And it's only 10 that it's the one I don't find. So I guess I'll have to use this just as the example. I come to a node that has no parent. And that node is not node 11. But I'm computing the 11th. If I'm computing the 11th row of the matrix L, that means I've put a non-zero here in my matrix L 1 through 11. So in T10, I don't have node 11. I just have 10 and its subtree. And here's node 11. It doesn't exist yet. But I've done the triangular solve, and I found that in the triangular solve, I see node 10, which is that non-zero. Well, that non-zero will become an entry in the 11th row of the L matrix, and that means if 10 does not yet have a parent, well, by golly, now it does. You see, if you come across a node that has no parent, suppose I have another node here that had no parent. If I do the triangular solve and I come across a node that has no parent, that means all of this is 0, but I found a non-zero here. So suppose this is position, this is going to be a different matrix. Suppose this is position 7. Okay, suppose I walk, this doesn't happen over here in this example, but suppose in this example, I have all zeros here. And I do the triangular solve on this piece of the matrix, and I find it's all zeros here, but I find in my solution, I find node 7 is in my solution. Node 7 will be in my solution, so when I slap it down here as the 11th row of L, that will be non-zero. That means there's an edge in the tree from 7 to 11. So as you're doing the elimination tree's traversal, as you're walking up the tree, and you come to a node and it has no parent, and it's not node K, well then K must be the parent of that node. And so that would be the way that we could actually compute the tree on the fly, one step at a time. I could change this algorithm to actually, and I mentioned this in the book, but I don't give the code. You can change this algorithm to compute the tree. You have to add a test in here that says, well, wait a minute. What if node, or where would it be? What if you come to a node here, and you realize that parent of I is not defined. So you can't make this next iteration. You can't go to the parent. So there could be a test here, for example. Hey, is the parent of I nothing? -1 is the nomenclature I use for nothing. If parent of I is -1, set parent of I to k. Because I've just put a non-zero in the kth row in this particular column I, and that's the first time I've seen column I, so parent of I must be k. What's that?
It looks like you're marking k right on top.
Yeah, it's marking k.
So it would happen.
But suppose I don't yet have the tree tk. Suppose I'm building the tree. If I'm building the tree, then there is no one has a parent k. Because all I have in tk minus 1, the tree for, this is just nodes 1 through k minus 1. Tk minus 1 does not have node k. So nobody's parent is k. So I'm only have this graph right here, say T10. So nobody has a parent 11. So what happens is you've got some subtrees here. It could be a forest. All right, but in the elimination tree of T11, it will include this row. But that row is the solution to the triangular solver, which you are just now doing. And so if you find, suppose this is all 0, and this is all 0 because it's nothing, there's no space there to be 0. Suppose you find that non-zero, and you find that non-zero. That means you traversed up this path and you stopped early. Oh. Speaking of stopping early, I'm now stopping late. So I'll stop here, making the parent of 7 and 10 k, which is 11. Because of these two new non-zeros right there. Okay, so we'll stop here and I'll pick up next Wednesday with elimination tree theorems.